today's goal of this lecture. Today I will see extension of Schwarz lemma, proof of extension of Schwarz lemma briefly. At first I will see maximum modulus principle and maximum modulus theorem. Okay, this is today's goal of this lecture. But at first I will recommend you, in my previous video I had defined it Schwarz lemma, not extension of Schwarz lemma, only Schwarz lemma. Briefly, if you don't see my previous video, at first see the previous video. I have given the link in my description box. What is the maximum modulus principle? If fz is analytic function, then modulus of fz does not attain maximum value in the domain unless it is constant. That means if function is constant function, then the maximum value exists in the interior of the domain. But if the function not constant, then the maximum value does not always exist in the interior point. When the maximum value exists in the interior point, then it is constant. That means maximum modulus principle tells about when the function is non-constant, when the maximum value does not exist, maximum value of fz does not exist in the interior. Max fz does not exist in the interior. But where the maximum exists, this does not tell maximum modulus principle. This tells about where the maximum value of fz exists when the function is non-constant. This part tells maximum modulus theorem. Maximum modulus principle only tells about when the function is constant, then maximum value exists of the function in the interior point. When the function does not constant, then the maximum value not be exist in the interior point of the function. Okay, z is analytic function and D is domain where D is bounded. Now my question, can fz is unbounded? Yes or no? This is my question. If fz is unbounded where domain is bounded, that means there exists singularity. And this type of singularity is either pole or essential singularity. As for example, fz equal to 1 plus z minus 1. On mod z less than 1, here domain is bounded. This function has a pole at z equal to 1. Also, if we consider e to the power 1 minus z minus 1 on mod z less than 1, then this singularity is essential singularity. Okay, that means when function is analytic function and the domain is bounded, then fz is unbounded, means there exists always singularity. But all of us know, if fz is entire function and the domain D is bounded, then if fz is entire and D is bounded, then always fz always imply this is bounded. But if fz is analytic where D is bounded, then it modulus of fz is unbounded. That means there exists one singularity, and this singularity exists only boundary point. Okay. Next, if fz is analytic and the domain D is bounded, then if fz is continuous on del D, that means if fz is continuous on boundary, then is there exist any singularity? Yes, it can be exist. If there exists a removable singularity, then if we remove the point of singularity from domain, then always function would be continuous on del D, on the boundary. So this singularity is known as removable singularity. If we remove the singularity from boundary, then function would be continuous on the boundary. Notice, maximum modulus principle does not tell us about where the maximum value exists if the function is not continuous. So, I will say about maximum modulus theorem. Maximum modulus theorem tells about maximum value where exists when the function not be constant function. Maximum modulus principle is, suppose fz is analytic function in a domain D and continuous on the domain on the del D, then modulus of fz, which is always reached and attains a maximum value always on del D. Furthermore, modulus of fz does not attain a maximum at interior unless fz is constant. That means if fz is analytic function in a domain D and continuous on del D means boundary, then the modulus of the fz, which is always reached maximum value exists on del D, on the boundary, when the function is non-constant function. Means here tells about maximum modulus theorem is tells about fz is analytic, the domain D is bounded, and fz is always continuous on the boundary. Then that implies maximum of fz always attains on the boundary. This tells about the maximum modulus theorem. What is the minimum modulus principle? Suppose fz is analytic function in a domain D and fz is not equal to 0 in domain D, then modulus of fz cannot attain minimum in the domain D unless fz is constant. If fz is also continuous on del D on the boundary and D is bounded, domain is bounded, then fz attains minimum on the boundary. That means when the boundary is continuous and the domain is bounded, then fz always attain minimums on the boundary. Similar to maximum modulus theorem, here one thing added, here fz always not equal to 0 in the domain. If fz equal to 0 in the domain, then fz cannot attain minimum in the domain. Okay? Here one thing added for minimum modulus theorem, here fz is not equal to 0 in the domain D. Here also fz is analytic, and here one thing added, fz not equal to 0 and D is domain which is bounded. Then minimum value of modulus of fz always attains on the boundary del D. If minimum value of fz attains in the domain D in the interior point of the boundary, that imply fz is constant function. Next theorem, let f be holomorphic function on the unit disk D. And suppose modulus of f greater than equal to 1, this is true on the domain D, and f0 equal to I, then which of the possible value of f of half? Option 1 minus I, option 2 I, option 3 1 and option 4 minus 1. Here modulus of f greater than equal to 1 on the domain D, that means that imply 1 always less than equal to modulus of f. That means minimum value of modulus of f equal to 1. Now we have to show where this minimum value exists. If this minimum value exists in the domain, then we can tell the function is constant. If this is exists on the boundary of the domain, then function is not constant. Here given f0 equal to 1. Then modulus of f0, this value is modulus of I, this value also 1. Since minimum value always 1 and modulus of f0 also 1, that means function is constant function. F be a constant function. Have you understood? Since the minimum value of the function is 1, also in interior point the value of f0 is also 1, and this is actually the minimum value. Since minimum value exists in the domain, interior of the domain, that means function is constant. Since function is constant, since f0 equal to I, that means obviously f of half equal to also I. I hope my all viewers have understood clearly this question. Okay, OA. Now I will see our main goal of this lecture, Schwarz lemma. What is Schwarz lemma? This is the extension of Schwarz lemma. In my previous video, I had discussed Schwarz lemma briefly, and this is the extension of Schwarz lemma. At first, I will highly recommend you, if you don't see my previous video of Schwarz lemma, at first see this video. I have given the link in my description box. This is the extension of Schwarz lemma. Let's see. Suppose fz is analytic function on mod z less than r with the condition f0 equal to 0 and modulus of fz less than equal to m in mod z less than r. If these conditions hold, then by Schwarz lemma, f prime 0 less than equal to m by r and modulus of fz less than equal to m mod z over r, and this is true for all z less than r. And if equality only holds, then modulus of fz equal to m over r e to the power I alpha z, if the equality holds. Let's see the proof. In mod z less than r, the function fz is analytic function about z equal to 0. Now open the Taylor series. About z equal to 0, then this would be fz equal to f0 plus z f dash 0 plus z square by 2 f double dash 0, so on. And since given f0 equal to 0, then this would be fz equal to z f dash 0 plus z square by 2 factorial f double dash 0 plus so on. Next, this part is true for mod z less than r. Here also mod z less than r. Then we can write fz equal to just common z, f dash 0 plus z square by 2 factorial f double dash 0, so on. And also this is true for mod z less than r. Then this would be fz over z equal to f dash 0 plus z square by 2 factorial f double dash 0 plus so on. And this is true since here fz over z, so at the point 0 the function is undefined, so this is true 0 less than z less than r. Now gz, consider new function gz equal to fz upon z when z not equal to 0 and f dash 0 when z equal to 0. And this is true for mod z less than r. Obviously notice gz is analytic function and here the domain is defined for mod z less than r, that means domain is bounded, D is bounded. And notice here given fz less than equal to m, which is true for mod z less than r. Now my next question, is there exist any singularity? Here the function is bounded for mod z less than r. That means if there exists any singularity, then this is actually the removable singularity. Because if you remove the singularity, then function would be continuous on the boundary. That means gz is also bounded function, and since gz is bounded, that means this is continuous on boundary. If not continuous, that means there exists removable singularity. If you remove the singularity from boundary, then obviously this would be again continuous on boundary. That means since gz is bounded, that means maximum of gz exists, and this is exist on the boundary mod z equal to r. That means maximum of gz, which is fz over z modulus. This is since fz less than equal to m, so this is less than equal to m, and mod z, this is mod z, and mod z is less than equal to r, so this is m over r. That means maximum of gz always less than equal to m over r. That means gz always less than equal to m over r, and this is true for all z belongs to r. And gz means fz over z, this is less than equal to m over r, and this is true for 0 less than z less than r. If we multiply both sides by mod z, then this would be mod fz less than equal to m over r times mod z, and this is true mod z less than r. And since gz is less than equal to m over r, then that implies g0 also would be less than equal to m over r, and g0 means f dash 0. So that imply f dash 0 would be less than equal to m over r. Okay, that means here I have got these two proved. F dash 0 less than equal to m over r, and fz, modulus of fz less than equal to m times mod z over r. This is true for mod z less than r. Now I will see the general version of Schwarz lemma. Suppose fz is analytic on mod z less than r with the condition f0 equal to 0, f dash 0 equal to 0, with fn minus 1 equal to 0. And if modulus of fz less than equal to m in mod z less than r, then here since 0 means here nth order 0 exists. So fn 0 divided by n factorial less than equal to m over r to the power n, that imply fz, modulus of fz less than equal to mz to the power n divided by r to the power n, for this is true for mod z less than r. If the equality holds, then fz equal to m over r to the power n e to the power I alpha times z to the power n. This is the general version of Schwarz lemma. This proof is same like before, only since here f to the power n and here n order 0 exists. So just we have to here consider fz equal to z to the power n fn 0 over n factorial plus z f n minus 1 0 divided by n plus 1 divided by n plus 1 factorial, so on. And we have to consider gz equal to fz over z to the power n when z not equal to 0, and when z equal to 0 we have to consider fn 0 over n factorial when z equal to 0. Now try to oneself this proof. Okay, well, today I will stop here. In my next video I will discuss some exercise about Schwarz lemma. Then you will understand Schwarz lemma briefly. Okay, at first see the proof of Schwarz lemma. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.